There is a fabric sitting in a museum right now that is 3,000 years old, still intact, still flexible, stronger by weight than the steel in your car door. It was engineered by a woman whose name most history books skipped entirely, and she is just one of seven. 7 women from ancient China who solved problems so precisely that we are still, right now, in the age of satellites and supercomputers, working to catch up to what they figured out with bronze, silk, and pure spatial reasoning. This video is a technical audit of how far we have not come. History has a habit of recording what was built and forgetting who built it. Nowhere is that gap more visible than in ancient China, where some of the most consequential technical breakthroughs in human history came from women who were either anonymized, credited to the men around them, or buried so deep in footnotes that you would need years of research to find them. 7 women inventors, so clever, we still can't beat them. Let's get into it. What does it mean to solve a problem so completely that 4,000 years of progress still hasn't produced a better answer? Leizu, consort to the Yellow Emperor around 2700 BC, didn't just find a useful fiber. She cracked a protein chemistry problem that modern materials scientists are still studying. The silkworm cocoon is held together by 2 distinct proteins: sericin, the outer glue that binds the cocoon's shape, and fibroin, the structural thread inside. The problem is that you cannot simply boil the cocoon and expect both to cooperate. Too little heat and the sericin stays locked. Too much and you destroy the fibroin entirely. What Leizu identified was the precise thermal window, the specific temperature at which the outer layer breaks down while the inner fiber survives completely intact. She did this without a thermometer, without a laboratory, and without a single reference text. What comes out of that process is not just thread. It is a material with tensile strength greater than steel by weight, natural resistance to UV degradation, and a molecular structure so stable that silk garments recovered from tombs sealed over 2,000 years ago are still intact and still flexible today. Pull a polyester shirt out of your closet. It begins shedding microscopic plastic fibers the first time you wash it. Within a decade, it structurally falls apart. Leizu's thread, by contrast, has been found in burial sites across Central Asia, still holding its structure, still carrying its original dye. But the thread itself was only the beginning. What made her contribution genuinely civilizational was that she didn't stop at the material. She engineered the entire system around it: the cultivation of mulberry trees to feed the silkworms, the precise harvesting window before the moth emerges and breaks the filament, the reeling process that unwinds a continuous thread up to 900 meters long from a single cocoon, and the weaving techniques that turned those filaments into fabric. She didn't invent a product. She invented an industry, one that would eventually become the foundation of the world's first intercontinental trade network. Here is the assumption worth questioning. Nylon, polyester, and acrylic were all marketed as improvements on natural fibers. They are cheaper to produce at scale, but they are environmentally destructive, structurally weaker over time, and in the categories that actually matter, tensile strength, breathability, longevity, they do not match what Leizu engineered from a silkworm cocoon nearly 5,000 years ago. We didn't improve on her material. We found a cheaper way to make a worse one. In computing, parallel processing means running multiple tasks at the same time rather than one after another. It is the core principle behind every modern processor. Huang Daopo built it into a foot-pedal textile machine in 13th century China, and she did it without a single line of code. To understand what she actually built, you need to see what she was working against. The standard spinning wheel of her era was a one-thread machine. One operator, one spindle, one thread at a time. Output was entirely capped by the speed of a single human hand. Wang Daopo redesigned the mechanism entirely. Her 3-spindle wheel used a foot pedal cam and crank system. The foot drives the cam converts that motion into rotation, and the rotation drives 3 spindles at once. One operator, one pedal stroke, 3 threads. The output tripled, while the energy input stayed exactly the same. The spinning wheel was only half of what she brought. The other half was a cottonseed separator that removed seeds from raw fiber using weight ratio mechanics. Rollers calibrated so that cotton fiber passed through, while the heavier seeds were rejected. No electricity, no external power of any kind, just the precise relationship between mass, geometry, and gravity, industrial output on zero energy input. She didn't arrive at these innovations alone. She spent years living among the Li people of Hainan Island, a community whose textile knowledge was generations ahead of the mainland. When she returned home, she didn't just bring the tools, she taught them. She trained an entire regional workforce, standardized the methods, and within a generation turned her home region into one of the most productive textile centers in the country. The conventional story places the Industrial Revolution in 18th century England. Steam engines, cotton mills, mechanized looms. But the conceptual core of that revolution, parallel mechanical output, energy-efficient separation, systematic workforce training, was fully operational in a Chinese village 400 years earlier. We didn't invent industrialization, we just made it louder. Some people, when they encounter a system they cannot understand, accept the confusion and move on. Wang Zhenyi was not that kind of person. When the official astronomical texts of her era stopped making sense, she didn't defer to the scholars who wrote them. She built a physical model and tested the math herself. She was born in 1768 AD into a family with a library, already unusual for a woman of her time. The astronomical scrolls available to her were dense, written in a mathematical language that even trained scholars found difficult to verify. The calculations for predicting eclipses and equinoxes were theoretically correct, but locked inside a format that almost no one could independently confirm. Wang Zhenyi looked at that situation and decided the problem wasn't the astronomy, it was the presentation. So she built a simulator. In a garden pavilion, she hung a lantern from the ceiling to represent the sun. She placed a round table in the center to represent the earth. She held a mirror at various angles to represent the moon. Then she moved them, slowly, precisely, in the geometric relationships the scrolls described, until the shadows and reflections matched the predicted positions of celestial events. She was doing spherical trigonometry with her hands, turning a mathematical black box into something you could walk around and verify. Her model predicted equinoxes, solstices, and lunar eclipses with up to 99% accuracy. The official imperial calendar of her era had documented errors. Hers did not. She also wrote about her methods, not in the dense language of the official texts, but in clear prose designed to be understood by anyone willing to engage with the logic. She believed that knowledge trapped inside complexity was knowledge wasted. She died at 29. In 11 years of serious scientific work, she produced verified astronomical predictions, written treatises on mathematics and geography, and poetry that is still studied today. The question her life raises is not what she could have done with more time. It is what we are doing with all of ours. Consider this. Today, anyone with a phone can open a real-time model of the solar system. Almost no one can explain why it works. Wang Zhenyi had no software, no formal education, no institutional support, and no scientific community that took her seriously. And she understood the sky more precisely than most people who stare at it through an app ever will. The tool is not the understanding. She proved that. For most of human history, fire was not something you carried. It was something you maintained, a continuous, fragile thing that had to be kept alive because starting it from scratch was slow, unreliable, and entirely dependent on dry conditions. The women who changed that were not scientists in any formal sense. They were palace workers in the courts of the Northern Qi dynasty around 577 AD, referred to in historical records simply as light-bringing slaves. Their job was to ensure fire was available on demand, anywhere in the palace complex, at any hour. The solution they developed is a piece of chemistry the modern match industry has not fully replicated. The mechanism was precise. Pinewood sticks were impregnated with sulfur at a specific ratio, not coated on the surface, but saturated through the wood fiber, so the sulfur became part of the material itself. Sulfur ignites at 248 degrees Celsius. By embedding it into the wood, they created a chemical trigger, a material that would catch from a much smaller initial heat source than untreated wood required, and sustain that ignition reliably once started. The result was a portable fire-starting device that could be stored indefinitely and used in conditions that would defeat every alternative of the time. Modern safety matches use a red phosphorus, striking surface that reacts with the match head on contact. In controlled environments, the chemistry works. In high humidity, rain, fog, the sealed interior of a siege fortification, the phosphorus absorbs moisture, and the reaction becomes unreliable. The sulfur-impregnated wood these women developed was not sensitive to ambient humidity in the same way. It worked in damp siege conditions, in monsoon weather, in the kind of environment where a modern match fails on the first strike. Think about what that means in a military context. An army cut off from resupply, sheltering in a mountain pass during a rainstorm, needing fire for warmth, for cooking, for signaling, and carrying a fire-starting technology that simply works regardless of what the weather is doing. That is not a convenience. That is a strategic asset. And it was developed by women whose names were never recorded, whose contribution was filed under palace administration, and who history has largely forgotten. These women were doing applied chemistry, working with ignition points, material saturation, and environmental stability in the 6th century AD, with no formal framework for any of it. They arrived at the right answer through observation, testing, and refinement. That is the scientific method. We just gave it a different name later. Lady Fu Hao is one of the most documented women in ancient Chinese history. A military general, a high priestess, and one of the most powerful figures of the Shang dynasty, around 1200 BC. Most writing about her focuses on her military record, which was extensive, but buried in the archaeological record of her tomb is a piece of bronze engineering that deserves its own conversation. The Sanlian Yan, the triple steamer, is a tiered bronze cooking vessel recovered from her burial site. On the surface, it looks like a stacked pot. What it actually is a heat recycling system. Here is the problem it solves. When you heat water in a standard vessel, steam rises, does its work, and escapes. The energy that produced that steam is gone. A modern steamer operates on exactly this principle. Water boils at the bottom, steam rises through a perforated tray, food cooks, steam dissipates into the air. Research on standard commercial steamers shows that roughly 60% of the thermal energy generated is lost through the sides and top of the vessel. You are burning fuel to heat the room. The Sanlian Yan was cast with intentionally varied wall thickness across its 3 tiers. Thicker walls at the base retain heat longer. Thinner walls at the upper tiers allow faster heat transfer to the food. The geometry of the internal chambers creates a pressure difference that causes steam to circulate, rising, condensing on the cooler upper surfaces, and falling back down to be reheated. The system feeds itself. Steam that would otherwise escape is captured, redirected, and reused. The practical result was that the Sanlian Yan could cook 3 separate meals, in 3 tiers, at 3 different temperatures, using the fuel a standard vessel would require for one. That is a tripling of output from the same energy input, achieved through the geometry of a cast bronze object made 3,000 years ago. Modern pressure cookers and convection ovens approach this principle from different angles. But a standard home steamer, the kind sitting in most kitchens right now, is thermodynamically less efficient than that bronze vessel. We have better materials, but we have not produced a better design. There is a concept in modern engineering called anti-fragility, systems that don't just withstand stress, but actually function better because of it. The term was coined in the 21st century. The principle was built into a floodgate in ancient China by a woman named Lady Zhu, and it has been working without failure ever since. The problem she was solving is one of the oldest in agricultural civilization. How do you protect farmland from seasonal flooding without building a system so complex it fails the moment conditions become extreme? The standard approach, then and now, is active intervention. Gates, sensors, operators, pumps. And when the flood arrives, you hope the power stays on, the sensors are reading correctly, and the operators are in position. Lady Zhu's approach was structurally different. She designed drainage sluice gates triggered not by human action or mechanical sensors, but by the weight of the water itself. As the water level rose, the pressure against the gate increased. At a precisely calibrated point, that pressure became the key. It physically opened the drainage sluice, allowing water to flow out through a controlled channel. When the level dropped, the gate closed. No operator, no power source, no sensor. The flood provided the energy and the signal for its own management. This is what makes it anti-fragile. A modern flood control system is most likely to fail precisely when conditions are worst, when the storm is strongest, when the power is most likely to go out, when the operators are hardest to reach. Lady Zhu's gate had no failure mode tied to external conditions. The worse the flood, the more pressure on the gate, the more reliably it opened. The problem made the solution work better. Modern engineers studying passive hydraulic design have arrived at similar principles. Flood barriers that use water pressure as the activation mechanism rather than fighting against it. They call it innovative. It was standard practice in Leizu's irrigation system over 1,000 years ago. We have built flood management systems of extraordinary complexity. Sensors, motors, control rooms, backup generators, redundant circuits, and they fail in major storms with regularity. Leizu built a system with no moving parts beyond a hinge, no external energy requirement, and no operator dependency. By any practical measure, it is still the more sophisticated solution. Princess Pingyang, daughter of the founder of the Tang dynasty, raised and commanded her own army in 617 AD. She is one of the few women in Chinese history to receive a full military funeral with battle honors. But the contribution that belongs on this list is not her battlefield record. It is the logistical architecture she built to make that record possible. Mountain warfare has one consistent vulnerability: supply lines. An army that cannot move food, weapons, and equipment through difficult terrain is an army that stops. The terrain of Pingyang's campaigns was unforgiving. Steep passes, narrow paths, no roads in any modern sense. The heavy wagon-based supply systems that conventional armies depended on were completely impractical. A single collapsed pass, a single washed-out trail, and everything behind it was paralyzed. Her solution was modular design applied to military logistics. She developed collapsible transport frames, structures that could carry significant loads across manageable terrain, but could be fully disassembled into components light enough to be hand-carried by individual soldiers over any obstacle. No minimum road width, no bridge weight limit. No terrain configuration that could stop the supply chain, because the supply chain could be taken apart, carried over the obstacle piece by piece, and reassembled on the other side. The strategic implication is straightforward. A conventional army supply line is a fixed vulnerability. Destroy the road, block the pass, take out the bridge, and the army starves. Pingyang's system had no fixed vulnerability. It adapted to whatever the terrain demanded rather than requiring the terrain to accommodate it. Modern military logistics has made significant advances in vehicle technology, aerial resupply, and real-time inventory tracking. But the core vulnerability remains. A modern military convoy is still stopped by a destroyed bridge. The solution to that problem, a genuinely terrain-agnostic supply chain, was operational in 617 AD. We have not produced a more elegant answer. We have produced faster, heavier, more expensive versions of the same rigid system she replaced. The principle she applied, that infrastructure should be modular and adaptable rather than fixed and powerful, is now considered a forward-thinking concept in humanitarian logistics and disaster response. Organizations working in post-earthquake and post-flood environments are rediscovering through necessity what Pingyang built by design 14 centuries ago. 7 women, 7 domains, 7 solutions that the full weight of modern engineering, chemistry, materials science, and logistics has not surpassed, only replicated at greater cost, with greater complexity, and with considerably less elegance. The pattern across all of them is the same. Without the luxury of brute force, they used precision. Without unlimited resources, they built systems that recycled what they had. Without institutional backing, they tested their ideas against reality until reality confirmed them. That is not a primitive approach to problem solving. It is the most rigorous one there is, and it produced results that are still standing, still functioning, and still worth studying. If the history you were taught left these women out, then what you were taught was an incomplete draft. And there is a great deal more where this came from. The next chapter is already in production, and the only way to catch it is to subscribe, so it finds you when it drops.